Hello and welcome to this topic, continuous mass distribution along a line. When I prepared this lesson at home, my son, a 7th grade student, asked me that, "Why do you teach moments and center of mass in college? We have already learned it in primary school." I asked him, "Did you study continuous mass distribution?" I said, "No." Then I said, "That's why we study it now." Generally, we deal with discrete mass in primary and middle school. Then we study continuous mass distribution with the help of calculus in university. Consider now a straight segment of thin wire of varying density. The density means mass per unit length, for which we desire to find the balance point. We impose a coordinate line along the wire and follow our usual procedure of slice, approximate, and integrate. Supposing that the density at the point x is delta x. So from the definition of definite integral, we first obtain the total mass. So by slicing it, we can find that each piece, we pick one piece, and the mass of this piece is delta x times dx. So we add them up, then we can find the total mass is this definite integral of delta x on the interval AB. And then we find the total moment. Likewise, the total moment is a definite integral of x times delta x on the interval AB with respect to the origin. This leads to this formula that x bar is equal to capital M over little m. That means the total moment over the total mass. So we have the quotient of the two definite integral. And there are two commands about it. First, remember this formula by analogy with the formula for the point masses. That is, the sum of xi times mi over the sum of mi. And in continuous situation, it's about the definite integral of x times delta x over the definite integral of delta x. Second, note that we have assumed that moments of small pieces of wire add together to give the total moment, just as the case for point masses. This should seem reasonable to you if you imagine the mass of the typical piece of length, delta x, to be concentrated at the point x. All right, let's see one example. Jordanson, could you read the problem and analyze it?
Example 1. The density delta x of a wire at the point x centimeters from one end is given by delta x equals 3 times x squared grams per centimeter. Find the center of mass of the piece between x equals 0 and x equals 10. Because we need to find the center of mass for a continuous mass density, so we apply the definite integral, similar to the formula for point masses. X bar equals capital M over little m, which equals sum of xi times mi over the sum of mi. We change the idea of sum, sigma, to the definite integral. Then we have the formula for continuous mass density. X bar equals capital M over little m, which equals the integral of x delta x over the integral of delta x. By solving the integrals, we can find the answer.
Thank you, Jonathan. Your analysis is so clear. Now let's solve it. Because the density delta x for this object is 3x squared, so the density is an increasing function. So we expect x bar to be nearer 10 than 0. Since the wire is much heavier, always say denser toward the right end. So according to the formula that x bar is the total moment over the total mass, that means the quotient of the two definite integrals. The numerator is the definite integral of x times delta x. Denominator is the definite integral of delta x. Then we plug in delta x and the upper and the lower limits. We will find the values of the definite integrals. And finally, to solve it, we will find that x bar is 7.5. Alright, we learned how to find the center of mass for continuous mass density by definite integral. That's all for this section. We're going to talk about more applications of integral in the following classes. I look forward to seeing you then. Thank you.